Hey everyone, here's part 2 of 2.5, and I'll try to do a much more concise and excellent way. So to review those questions, the point is try to figure out the graph you're talking about, try to understand what they're looking for, and make sure you don't make some number errors like I did on this one. Again, know your graphs. Know what the period will be for this graph. Know what the amplitude will be. Know what the shape will be. Know which direction it's pointing. If a function, so just understand the basics of that. And I've also brought up the answers for these questions. So if I look at the answers here, because it's much easier to verify the work. So of course, in this case, they used an h of 0.01, and they determined that the rate of change was close to 0. In number 2, which was about the sine curve, what is the rate of change when the blood pressure is 3 seconds? We also determined that. It was at the top of the slope, I think, which we proved was the peak of the coast curve and had a slope of 0. And then we also concluded this, number 3. If a function, and they took a random point on a function, and they said if that is indeed the top of it, what would you expect at the left? We would expect A, and they said if it's a maximum value, and we'd indeed said if it's to the left, we would expect the slope to be positive and close to 0, and if it's to the right, we would expect the slope to be negative and point to 0 if it's a maximum. And sure enough, that's the answers they gave. And then the reverse on the next question, we expect the opposite. On a minimum value to the left of the point, we expect the slope to be positive and close to 0. And to the right, we expect it to be negative and close to 0. And sure enough, that's what they concluded as well. Then in number 4, if a function, or number 5 rather, they gave each of these, and you essentially had to take the rate of change just to the left and the right of these points. And you indeed had to you were told if it was a maximum or a minimum, that it's a maximum or minimum for sure, and to figure it out. Well, the whole point is if the slope is negative on the left and positive on the right, it's a maximum. If it's positive on the left and negative on the right, it's a minimum. Exactly what question 4 was going over, question 3 and 4. So they're trying to get you to apply the knowledge you learned in 3 and 4 on these. And sure enough, they go over it and say the slope is 0, the slope is 0, the slope is 0, the slope is 0. So you're trying to get close to 0, but you should also look and see if you can apply the lesson learned in number 3 and number 4. And then, of course, the only way to do this was some basic logic. And in some cases, we could analyze the graph and figure out where these points were. And in some places, because we haven't learned the proper tools yet, we had to essentially just take the point immediately to the left and immediately to the right and understand the nature of those curves, which will play a bigger role in Chapter 3. Which brings us to number 7. A pilot is at the plane of 10,000 feet when he jumps. And there's a little trickiness here, because you would think, oh, well, 10,000 is the maximum, and he's going to just fall downwards from there. So 10,000 is the maximum. You might not understand the question, which says, what's the maximum height? But the trick here, which unfortunately these books sometimes do, is to understand that airplane fighter pilot injection seats actually go up and then down. So there's a good chance that while this graph, when time is 0, will indeed cross the y-axis at 10,000 feet, there's a good chance that if I were to graph this, and I'm not going to just yet, that when he first at time 0, he's at 10,000. How do I know he's at 10,000 at time 0? Because at time 0, this becomes 0, and this becomes 0, so I'm just left with 10,000. So I know that there's a spot up here that's going to be 0, comma 10,000. Also, what kind of graph is this? It's a downward-facing parabola, and the only information we have is that the y-intercept's 10,000. But I can also assume that he's going to eject upwards and then down. So it's safe to say in those first couple seconds he's going to be heading up, and then he's going to be heading down, and that's the only information we have. Estimate at what time the pilot is at the maximum altitude. So the good word there is estimate. We're not going to come up with an exact value. Explain how the maximum altitude is related to the slope on the tangent line. So I would say, come up with this. Find your h of 0, which means the height when time is 0, which we did. It's 10,000. Then find your height when time is 1, and that involves plugging 1 into the equation. So you get 1 squared times minus 16, which is minus 16. Then you get 1 times 90, then you get the original 10,000. So you can see that this first value is the only thing that could possibly lower the value of our 10,000 height, and everything else will be positive. So we won't start going down until that gets a little bit bigger. So what is this? It ends up being plus 74. So we get 10,074 is clearly the height at 1. Let's continue and do the height of 2. When I put 2 into the square, I get minus 16 times, what's 2 squared? 4. So that's going to be minus 64. We can see that number is getting bigger, plus 90. It's still not defeating the 90, though, and 10,000. What do I mean by defeating the 90? It's still not bigger than this 90, so I'm always going to have a height bigger than 10,000. So that ends up being minus 20, or plus 26. Oh, yeah, so we can see at height 2, is he going down? Did I get that right? Minus 4 times that, minus 13, minus 64. Oh, no, I didn't get it right. I didn't do the 90 correct. So we can do is see that the first number is indeed minus 64, but the next number is 90 times 2, which is 180. And when I subtract those two, I am left with 116 plus the 10,000. So I'm left with 10,016. So what's my height at 3? It's going to be minus 16 times 3 squared, which is 9, plus 90 times 3, which is 270, plus the 10,000. So the minus 9 times this is minus 9, and that's 54. So minus 144 plus 270. I can see that that's going to be 136. So I can see that my height is now 10,136. So I'm still going up because height 3 is higher than height 2. And it's a little tricky here because you might think, oh, well, it's after 3. When I do 4, however, I'm left with 4 squared times minus 16. 4 squared is 16. And 16 squared, oh boy, am I really that bad at my 16 times tables? I think it's, yeah, 256. I should have known that. Minus 256. And then it's plus 90 times 4, which is 360. When I subtract those, I get a value here of only 104. Oh, suddenly I get 10,104. The height is going down. Now, it'd be tempting to say that, therefore, the height, maximum height is somewhere between 3 and 4. Right? It'd be very tempting to say that. It's not necessarily true, because between here we could have reached a higher height and then been descending to that. The only way to find out is to look at the height at like 3.1. So we know something's happening somewhere around here. 3.1, if we put 3.1, we've got to do, and this is where Desmos is easier. Well, we'll do the calculator. So we do 3.1 squared times negative 16. In case you don't know what I'm doing, I'm just plugging that number into x, into t, wherever I see it in the equation, plus 90 times 3.1 plus 10,000. Suddenly I discover that my height has gone down at 3.1. So that means that 3 could be my max, or just very, very close to 3, or maybe on the other side, I should make sure of my height at 2.9. And this is where Desmos is good, because you can put this entire formula into Desmos and just write this, and Desmos will tell you these values over and over and over again. And it's also why you should learn how to use your calculator. So when I put 2.9 in there, and I square it, and I times it negative 16, and then I add, I got to click equals, and then I add 90 times 2.9. This is a value just before 3. Click equals, and then I add 10,000. And I shouldn't have to click equals. Your calculator should have order of operations. Oh, I discover if I did it right, I don't think I did it right, actually. I might have done it correctly. Let's try it again. 2.9 times 16 negative equals plus 90 times 2.9 plus 10,000. Yeah, I discover the height is lower. Actually, I hope it's true. I think I'm going to switch to Desmos to make sure I'm doing the correct calculations, because the earlier ones I was just kind of winging it. We discover it's this, which means there's a peak somewhere between 2.9, 3, and 3.1, and we're not sure where it is. Now, obviously, if I put this into a calculator, I'm going to get a good idea. But really, what I now should do is look at the rates of change to the left of some of these points and to the right. Because if the rates of change is positive to the left of, let's say, 2.9 and negative on the right, we know that the peak is somewhere in there. If I get a positive and positive on both sides, we know that the peak is somewhere else to the right. If I get a negative and negative on both sides, we know the peak is somewhere else to the left. So let's find out, and here's where I'm going to actually do a calculator. So I'm going to take a value for f2.9 somewhere just to the left, and I'm going to say my rate of change to the left of 2.9 is f of 2.9 minus h, so f of 2.9 minus the point just to the left, f of 2.9 minus h. Now, if the value of h is 0.001, then you can do this. Okay? In this case, it's 0.0. There's like 5 zeros. And all divided by my h. And this you'll need a calculator, because you're going to have to punch this in. And it's actually easier to do 2.9 minus the same value so that you don't screw it up. And so that means you're going to have to use a calculator to find your 2.9, which you already did over here on the left, and your 2.9 minus 0.001. So this is why I do like Desmos a little bit. And I'll just pull up another. Is that it there? Yeah, I'm going to hide the equation so that you don't see it. So this is it there. And here's my 2. And here's my 3. And then I discover 4 is going down. And so I'm going to take, let's just go straight to 2.9. Take 2.9. And now I can get rid of F4 because I know something's happening, and F2 and F1 because I know something's happening around there. So I can see my height at F2.9 is slightly bigger than that. So now I can even take my F2.8, and I can see the height is still a little bit bigger. That helps a lot. Now I can take my F2.7, and I can see my height is going down. So this is on the left of 2.8. It's a lower altitude. This is on the right, and this is on, this is in the middle, and this is on the right. And this point here is higher than the point on the left and the point on the right. So the peak is somewhere in there. Now, right away, we've already done it. But let's say I was convinced way back when that it was 2.9, and I was going to stick to my plan. My rate of change is going to be equal to that point, f of 2.9, minus a point just to the left of it, 2.9 minus what h did we take? We're going to take 4 zeros, all of it divided by that h. You can even make it simpler for yourselves and set an h, and also be sure to make sure you're in degrees. And because r is radius, we should take another thing, let's call it change. And we can see that point on the left is negative. So that means I've got a downward slope to the left of that point. If I have a downward slope, if this is my point, 2.9, and the left side is showing negative, that means it's going down. Well, that means 2.9 cannot be a maximum because the left side of it should be positive. So right away, by finding the negative, I know 2.9 is not the maximum. So we realize right there, maybe I should make 2.8 and see what's happening at 2.8. The left side of my 2.8 is positive, as I would expect it. Let's find my rate of change, C2, on the right side of it. So the right side of this F2.8 plus my H, 0.00001, minus my F of 2.8, because it's on the left, 2.8 is to the left of it, all divided by my H, 4 zeros. And I see on the right side it's still positive. which means 2.8 is not the peak either. So it's somewhere between 2.8 and 2.8. So I could do 5 now, 2.85. I discover that the rate of change to the left is negative, and 2.85, I discover the rate of change to the right is negative. So 8.5 isn't very good. So estimating round, it's somewhere around 2.85. We can try 2.7. Let's do 2.7. To the left is positive, and I think we've already proven that it's bigger than 2.8, so this is kind of useless. And the right is positive, so we can see with 2.8 and 2.7, we're getting a positive slope on either side of it, which means it's not the peak. And we found 2.85 doesn't work. So we're really talking about something really like 2.89, which makes it really hard to find it this way. So really we got to make maybe our gaps between it even bigger. So that's negative on the left side of 2.89. So we're really talking about a value that's bigger than 8.5, but smaller than 8.9. You can see it can keep going like this. So let's take a value, and let's assume, how would we find it? Well, we could keep taking values of f.2.8 and see which one's higher. So 2.89, f of 2.88, which one's higher? The 2.88. So we can get rid of 2.99. And we know everything to the left is going to be higher. So we're going to try 2.87. 8 versus 7. 7 is higher. 6 versus 7. 6 is higher. 5 versus 6. 5 is higher. 4 versus 5. 4 is starting to go down. So we can see 2.85 is probably the peak. Let's turn on our graph. And by the way, that's getting crazy accurate. Let's turn on a graph, and we're going to find the vertex. So I'm going to cheat and say, when is this 0 equal to f prime of x? And it's telling me right where that black line is. So 2.813. 2.813, and it's getting a 10. So that means somewhere between 8 and 8.82, yeah, is the peak. So even our fiddling around wasn't accurate. So I would say, the best one to do would be 2.8 and then just kind of estimate. Now let's see what the book says. The book says that around 2.75. So you can see that they really guesstimate on that one. Answers may vary. For example, the slopes of the tangents for values of less of t would be positive, while slopes of tangent for values greater than t would be negative. So I don't even think they were that accurate, because we saw that actually is not be true, because 2.5 is indeed not the slope. So it's sort of a guesstimate, as we did. So really you would find whereabouts you could strongly conclude that around 2.8 and somewhere about 2.85, it's somewhere in between there, because look, those heights are pretty much the same. If the heights are the same, it means it went up on one of them and is coming down on the other. So their answer, even in the book, isn't as accurate as fiddling around it is. But you can see that if you don't have the right data, you can only get an approximation. Okay, that's good enough. Graph each function using a graphing calculator. Let's look at them both first. That's a parabola facing up. That's a parabola facing up. That's a parabola facing down. That's a parabola facing down. Draw tangent lines on either side of the points. Explain how the tangent lines confirm the existence of minimum max values that you found on this. So you're allowed to just look at them. So x squared plus 10x minus 15. To me, you should actually be working with the graphing calculator first. It makes your calculation life easier. And you will also avoid all those errors that will actually teach you the wrong thing, right? Minus 15. Okay, let's get rid of all this other stuff. Let's go to home and find it. So you can see it's an upward facing parabola, and it's quite clear that the x value is minus 5. So we're going to take a rate of change to the left of minus 5. And what are we hoping the rate of change is going to be, positive or negative on the left of 0.5, minus 5? Well, we're hoping it's negative because it's sloping downward. So we're going to take this as they asked, and we're going to bring it up to here. And we're going to draw a tangent line just slightly to the left. And we're going to draw a green tangent line slightly on the right. What is the slope of the black line, which is a point to the left? It's negative. What is the slope of the green line, which is slightly to the right of the point? It's positive. And if you're saying, well, no, I can't really see that. If we were to draw a bigger curve or a gentler curve, right, like that, and I was looking at a point right here, it's quite clear if I was drawing the tangent line there that it would be like that. If I was a point here, it's quite clear that I'd be drawing a tangent like that. And you should already know the slopes when they're negative of lines and when they're positive. Lines that go down are negative, lines that go up are positive. So that's what they want you to do, and then they want you to confirm it algebraically. Well, that means we should take a value at minus 5, and we should take a value just to the left of minus 5. Right? Or let's just take minus 5 minus 0.0001, which is a value and we can see it's minus 39.9. Then we're going to take those two values to find the rate of change of that point. So you've got to do this point first because it's to the right. Subtract this point. All I'm doing is subtracting 0.001 from f of 5, and then we have to divide it by our h, which was the same as the thing we subtracted by. And we can see our slope is negative, as expected, and almost 0. Now we're going to do the same thing, but we're going to take the same value of f of 5, and we're going to take a value just to the right of it with the same h. And we're going to get 6 just slightly bigger than 60. Then we're going to find the rate of change between that point and the f of 5 point. And we're going to divide it by our h. And we discover, oh, I made an error somewhere. Oh, I had to name it C2. And I had to make sure I'm doing minus 5. Because that's our point. Okay, and we discovered, look at that, our rate of change is almost 0 and positive, which proves that on the, let's see, where was I? Which proves that the black line is close to 0 and is indeed negative, and our green line is indeed positive and close to 0. And that proves that minus 5 is most likely, not for certainty, but with approximation, is most likely minus 5. And why can't we conclude exactly? Because even with h, we don't quite have 0. We just have very close to 0. But there's very strong indications. Of course, the graph tells us, but they're trying to teach you how to figure this out. So what's the next one? It's an upward facing parabola, 4x squared minus 26x minus 3. 4x squared minus 16x plus 23, was it? I'll go back and look. No, minus 3. Way off on that one. So they're telling us the max. They're asking us to figure out the max. We can see the min, because it's an upward facing parabola. We can indeed see the min is 2.9. 2.9. Oop, I don't like doing it like that. Do it like that. And if we were to take a picture of it and put it over here, and we were to draw a point just to the left of it and draw the tangent line, we should expect it to be negative and close to 0. And if we were to draw a tangent line to a point just to the right of it, we expect the same thing. So it's very much the same thing. But the point they're interested in now is that x is 2. Well, we can see when x is 2, y is minus 19, which is indeed the case. So we're looking for a point that's just to the left of this, which is that point. You can see it's just below 19. And what we're going to do is we're going to look at that point that's just to the left of it. And the nice thing about having these formulas is we only have to replace these values. And we can see that indeed the point just to the left of it has a negative slope that's close to the 0. Let's take a point just to the right of it. This is the point just to the right of it. We expect it to be just slightly above minus 19, and indeed minus 19.999 is slightly above. Notice that the f of 2 minus this point and the f of 2 above this point, so I should use a different one. There we go. Are the same there and there. That's because we're equidistant on either side of the vertex. So then if I do the same thing, I'm going to find the slope of the point that's just to the right of this. Whoopsie. And that's because I zoomed in. There we go. And it's not negative 2, it's positive 2. I get a slope that's almost 0 and positive. And notice the slopes are the same, just their signs change. And that's because this point on the left is equidistant to this point on the right. And you'll find that any points you go up on equal sides of the vertex will have the same slope. For instance, this point here at 2.716 will have the same slope but opposite signs as this point because they're on opposite sides of the vertex at the same y value. So there again, we've proven it. Now what should we expect with these next ones? Well, these next ones are downward facing parabolas. They're downwards facing parabolas. This one here is a downward facing, and this one here is a downward facing, which means now if we look at the point on the immediately left side, we're going to get a tangent line that is positive. And if we look at a point that is immediately to the right, we're going to get a tangent line that is negative, or a slope that is negative on either side, and both should be close to 0. So the first thing is we plug this into a graphing, this one into a graphing calculator. Minus 3x squared plus 45x plus 16. Nice thing again is we'll have all the values ready for us, all the formulas ready for us. And you can simplify it even more by using h as a variable. 45x plus 45x, I think. That's how bad my memory is. Plus 16. And we can see from this graph our upwards facing vertex is way here. And if you can't find your vertex, you can always ask, yeah, you can just zoom out, but there's a way. Anyway, so now that we've discovered the vertex is f7.5, and we confirm that the y value is indeed 184.75, we can calculate a point that's just to the left of it. And notice that it's the same value here, except that there is going to be a slight difference. So we should probably take a value. There we go. I think we can get away with this so long as it doesn't round. Let's see if it'll round too far for us. So we're going to take the slope of that point that's just to the left, which we know is at 7.5x. And good enough, we do indeed get a slope that's close to 0 and positive. And that's the point to the left of the vertex over here somewhere, which is what we would expect, positive and close to 0. Then we're going to do the same thing, but we're going to take it for a point that's just slightly to the right. It looks like the same value. Just keep in mind that the Desmos is rounding it up, and you will see it if we were to take a smaller value for h. It looks like it's giving us the same value, but all it's doing is rounding up. And when we plug it in, we can see that it doesn't affect our answer. So we're taking this slope for a point that's slightly to the right of it. We're essentially taking the rate of change between 7.5 and a point that's slightly to the right. And we get negative and small. So we can see that indeed it did exactly as we expected. And what are they trying to teach you here? They're trying to teach you to understand the slopes. So indeed, for this point here, which is a point just to the right, left, is indeed almost zero. It's actually like this, but positive. And a slope just to the left is almost zero, but sloping down. And I'm exaggerating the slope so that you understand what I'm doing. In reality, the slopes would almost look, horizontal and flat. Oop. They would almost always look close to the actual peak. But it just goes to show that the very peak of a vertex, or the very min, should be zero, the slope of the tangent line to the vertex of anything, any peak. Remember that. Okay. And of course they get us to prove it once again. Why do we have to prove it over and over again? So that during a test or during actual work, you won't make a mistake. So this one's minus 0.5 squared, so it's pointing down. It is indeed. You can see sometimes this is tedious, but you're lucky. In my day, we didn't have graphic calculators, or they were just coming in anyway. So you had to do it all by hand. Okay, plus 0.5, 0.45, I think it was. I'll go back and make sure because I've been making lots of technical errors lately. So if we look at this graph now, hit home button sometimes will help you find it. You can see the peak is right there at 6.8. 6.18. So that means at 6.18, that's the point I'm trying to go to the left and right of. So I'm going to try to find a point that's just slightly to the left of that. And we can see indeed it is slightly smaller than this. Oh, interesting. Let me make sure that that's the vertex. It's 6, so my mistake. It is at 6. I was accidentally putting the y value in there. It's 6. So that means I'm going to take a value slightly less than 6. And I'm going to put it in my rate of change calculator here. So I'm taking the rate of change between f of 6 and a point slightly to the left of 6 divided by 6. And it's essentially just a delta y, delta x divided by delta x. And I see almost 0 and positive, which is what I would expect. Then I'm going to take a value slightly to the right of 6, and I'm going to put it in my change calculator. I'm going to take the point slightly to the right, minus that point. Those are the y values up here, divided by the x change, which is always just my h. And I see a negative almost 0 slope, identical to this one because it's equidistant on either side. So indeed, I've confirmed once again, if I were to draw it, that I have a slope that's going down and almost 0 on the right side, and a slope that's positive and going up on the left side and almost 0. And that's all you're trying to learn from this. Find the maximum and min values for each exponential growth on the given interval. This is bizarre, a bizarre question. And by the way, we should confirm our answers. Always confirm your answers, but I'm not going to for the last one because we had a graphing calculator working for us. So this is a bizarre question, and I hope I'm doing it right, and I should probably make sure I understand what they're asking. But for me, you have to remember your basic curves. How do you identify a growth curve? Well, its base to the power of x will always be above 1 when it's a growth curve, and it'll always be below 1 when it's a decay curve. And growth curves and decay curves all behave the same way. So growth curve will always start small and get big, like that. But it'll always be increasing as I go from left to right on the x chart. Y will always be increasing. It doesn't do like a sine curve. It doesn't go up and down. So for me, anything on the left will be smaller y value than anything on the right. And the slope will always be positive on a growth curve. How do you identify a decay curve? When the base is smaller than 1. And a decay curve will always look like this. Always, always, always will always look like this. And the same thing, except opposite. As I go left to right on my x values, y will be going down, which means if I take a point from here to here, doesn't matter where I take it, by the way, I will always have a negative slope, and this point will always be higher than this point. So that's just common sense. So let's identify which one is a growth and which one is a decay in y. Always pause and do it for yourself if you know. So this one is 0.85 is the base. The base is always the thing that's to the power. Okay, and they're doing this based on y is equal based on t, so time, I guess. And since it's at 0.85, is 0.85 smaller or bigger than 0? Or smaller or bigger than 1? It's smaller than 1. Therefore, we have a decay curve, which means since 0 on the x-axis is measured in t, since they're asking us from 0 to 5, the 0 value will always be higher up than the 5 value, which is further along the t or x-axis, which means this will always have a higher value than that, which means the slope is of any rate of change between those 2 points will be negative. So looking at the question, find the maximum and min values for each exponential growth or decay curve in the given intervals. Well, between 0 and 5, the maximum's always going to be at 0 and the minimum's going to be at 5. And technically, it's not really a minimal. If you keep going, it gets smaller. It's just the minimal value between those two values. So I don't quite understand why they're asking this question, but I'm going to do a quick look at this answer to see if that's what they're getting at. And sure enough, the point at y will always increase as x increases for any equation that represents exponential decay. So the minimum value will always be at point B, and the maximum value will always be at point A, which means what I'm saying. For a decay curve, any point that's to the left will be a max value, and any point to the right of that point will be a smaller or a min value. And I guess what they're trying to get at is for you to recognize when you're dealing with growth or decay, for you to spot it. Now let's look at the next question. And it is clearly, is this a growth or a is this a growth or is this a decay curve? So now we're looking at this one. Is 1.15 bigger or smaller than 1? It's clearly bigger. Therefore, we're dealing with a growth. If we're dealing with a growth curve, we're dealing exactly with what I said before. And you can always punch these into Desmos to prove it. And all growth curves are like this. Oops. They all start small, and they all get higher values of y as x increases. So that means, since this value of x is on the left, 0, and this 10 value is somewhere over here, 10, the value here of y is going to be lower than the value here of y. So that means this will be a min value and this will be a higher max value for a growth curve. And then they ask the general question, examine your answers for part B and use to hypothesize the range between A and B. So instead of 0 and 10, they're saying A and B. So the answer, as said in the book, for growth curves, the value at x is equal to A will always be smaller, the y value, smaller or minimum, compared to B, which is a value to the right of A. When x is equal to B, the y value will be larger compared to f of A as you go left to right. And this is true, and they generally always go left to right as x increases. For decay curves, the opposite is true. the y values for f of a will be bigger or maximum compared to the y values for f of b when b is to the right of a, which just means when I'm taking 2 points and I'm calling a to the left and b to the right, on growth curves, b's y value will always be bigger, and on decay curves, b's y values will always be smaller. That's all it means. This will always be a max, this will always be a min when the 2 points are an interval to one another. I think they're getting you used to that just so you can analyze data on growth curves. Now there's a few more questions. 10. The height of a diver above the water is modeled by the function. So he's probably going up a little bit and then down, where t represents the time in seconds and h represents the height. Use the appropriate calculations to calculate the rate of change in height to show that the diver reaches her maximum height at t.5. So they're essentially telling you the maximum is when t is equal to 0.5. Now, I'm going to put it into decimals, but not with the graph. So minus 5t squared plus 5t plus 10. Minus 5, and I'm going to turn it off. So minus 5t squared, and I'm going to do f of t, and minus 10t plus 10, let's go back, plus 5t plus 10. Okay, and they're saying that at 0.5 seconds, he's going to reach the max height. And I believe it was 0.5, yeah. And to prove it, well, at 0.5 seconds, his match height is 11.5. Now, we could just take values left and right of that to figure it out. But we're going to do it using slope. So if that's the max height, the slope just to the left of it, since it's a maximum, should be positive and close to 0. And the slope just to the right of it should be negative and close to 0. So there's 2 ways I'm going to do it. I'm going to take f of 0.5 and I'm going to find a value just to the left of it. And we can see it's just barely below that y value, which is a hint. And then I'm going to take the point, f.5, and I'm going to subtract that y value. And then I'm going to divide it by my h to come up. Oh, sure enough, look at that. It's positive and almost 0. Now I'm going to find a point just to the right of 0.5, and I can see, look at that, it's also just below that y value, which is a huge indicator. Since this is below, and they're on either side, and they're the exact same amount, it's a huge indicator that that is indeed the max value. But I'm going to go ahead and punch it in. I'm taking a point just to the right, subtracting it, and sure enough, I see my slope is negative and 0.5. So now I'm going to put it in there. And sure enough, if I look, my vertex is indeed 0.5, 11.25, and I can prove, looking at these calculations, that indeed, this one has more zeros because I added more zeros in it. So I should use the same h. I can see that they are also the exact same slope, but opposite signs, which is also an indicator. And it's almost certain that 0.5 is the max. Not 100% certain, though, because this is just an indicator. We're sort of getting close, but not perfect. When you graph it, you let it graph out, yeah, you discover it. And if you were to complete the square, you might say, why am I doing this when I can just complete the square? Well, because obviously you're going to come across more complex graphs that you can't complete the square of. So if we were to complete the square of the first 2 values, I would take minus 5 out, and I get t squared plus 1, minus 1, and then the plus 10 stays over here. And I can see right away, just by partially completing the square, that the value that partially completes the square would be t minus a half, because it's always a half of this squared. This tells me right away that my x value is indeed positive 0.05, because it's the opposite of this one, for the vertex. Well, so right away I can confirm that x.5 is indeed going to be the vertex, because the completion of the square tells me the vertex. And the beautiful thing about partial completion of the square is all I need is the x value to confirm that. Okay, onwards. There's two ways of doing it. So we have a top of a flagpole. First of all, how is it modeled? Well, it's using a sine curve. Let's understand that sine curve before we answer the question. And this will help you a lot. Sometimes you can do it, sometimes you can't, but I'm doing it to show you that it helps your analysis to understand the graph. Okay, well, we know a sine curve normally starts at 0, 0. And we know it goes up and it reaches the max of 1 at 90 degrees. Then it comes back down, it reaches the bar again, the axis, at 180 degrees. Then it goes down, it reaches minus 1 at 270 degrees and comes back up at 360. It's a height of 0 again. So 0 twice, three times if you count the origin. So this is important knowledge to have of your parent graph. If you don't know it, know it. This grade is full of sine curves and cosine curves. Now you just have to remember your translations. And the nice thing here is there's only two translations. One is a y translation, and one is an x translation. Well, this, we know, changes the amplitude. So instead of a maximum of 1, and since there's no axis change here, we know the x-axis is still the axis. So instead of 1, we know the max value is going to be 8, which means the min value is going to be minus 8. We also know the period's been changed. This changes the period. And you might say, oh, it's 180 times 360, but if you remember, it's actually going to be the opposite. What's the reciprocal of 180? 1 over 180 times 360, which is essentially 360 divided by 180. What's 360 divided by 180? It is 2, which means my period is no longer 360, but for it to complete one complete period, it takes 2 seconds. It takes 2 seconds. So one complete period is 2 seconds. Now this also helps you to understand this main graph, because the main sine curve is not going to change. It's going to hit a max at a quarter of the way through, the axis halfway through, the minimum 3/4 of the way through, and back up to 0 once the period is complete. Well, if I look at this, these are quarters. And if I divide this into 4 quarters, it means this first part hits a max after 0.5 seconds. It will come back down to the minimum at 1 second, which is the halfway point of 2 seconds. At this point, it'll hit a min, which is 1.5 seconds. And then it'll come back to complete its period at 2 seconds. If you don't understand that, you need to understand that a sine curve has the same pattern over and over again. And for me to do it properly, I would have to put my x values in 360 to get an idea. And that means that at a quarter, it's always going to hit the max. And halfway, it's always going to hit the axis. And 3/4 of the way through, it's going to hit the min, and all the way through, it's going to hit the max. Well, if that's true, that means that a quarter of the way through, it's going to hit my max. What's a quarter of 2 seconds? Use your calculator if you have to. A quarter times 2 is 0.5. Which means at 0.5 I'm going to hit my max. What's my new max that we determined? 8. So instead of 90, 0, I'm going to have, at 0.5 seconds, a maximum of positive 8. Then, what's half of 2 seconds? I already said that at a halfway point, it comes back to 0. And since this is not adjusted up or down, it's going to come back down to 0 at half of 2 seconds. What's half of 2 seconds? It's 1 second. So at 1 second, we're going to hit the axis again. And then down here, I've told you that this is the 3/4 mark. What is 3/4 of 2 seconds? If I take 3 over 4 and I multiply it by 2, the 2 will cancel out with the 4, and I'll get 3 over 2, What is 3 over 2? It's 1.5. So at 1.5 seconds, I'm going to hit my new min, which is minus 8. Now, the interesting thing about this is you now have to understand that these values will repeat every period, every 2 seconds, which means I'm going to hit my max at 0.25, but I'm also going to hit my max at 2.5, 4.5, 6.5, and I'm just adding the period over and over again. I'm going to hit my min at several places. I'm going to hit my min here and here. So I'm going to hit it at 0, and I'm going to hit it at 1 second, which means I'm going to hit, my axis, which means I'm going to hit my axis at 0, 0, 0, or 1, 0, and I'm going to add 2 seconds to both of those. I'm going to hit it again at 2, 0, and 3, 0. I'm going to hit it again at 4, 0, and 5, 0, which means I'm hitting it every second. I'm hitting the axis every second. So I can just write it. I'm going to hit the axis at 1 second. I'm going to hit the axis again at 2 seconds, which is proven already. 3 seconds, 4 seconds, 5 seconds. So since it hits the minimum at 1.5 seconds, when else is it going to hit the minimum? Well, we just add 2 seconds. It's going to hit the minimum at 3.5 seconds. It's going to hit the minimum at 5.5 seconds. It's going to hit the minimum of 7.5 seconds. This is an important skill to learn, to understand that these max and min values and axis values repeat over and over and over again every period. And they also continue in the negative zone, so as we go backwards in time. Now let's look at the question. The question says, where a flagpole goes back and forth, the function f of t is represented as we just described it. Represents displacement, which means where the flag is flying, in centimeters. The flagpole sways from vertical, where t is in time. So they're calling the middle point, they're calling the axis vertical. So whenever it hits 0, that's vertical, and the flag either is going to sway one direction or sway the other direction as it flaps in the wind. The question is up left or is up right? The flagpole is vertical when f of t is equal to 0, so they're telling us the axis. It is 8 centimeters to the right at its resting place when f of t is equal to 8, which we know is a maximum. So that means the maximum is considered right. And it's 8 centimeters to the left of vertical of its resting place when it's at the minimum value, minus 8. So that means on our graph, top values, max values, are considered to be right of center, and minimum values are considered to be left of center. So it's always important to understand what they're asking. If the flagpole is observed for 2 seconds, it appears to be the farthest to the left when t is 0.25. We've already determined that left is min value. So the question is, does min value occur at 1.5? Is this observation correct? Justify your answers using rate of change. So I'm using it first graphically so you understand. So the question is, at 1.5, are we at the minimum? We've already determined that at our 3/4 spot, we are indeed at the minimum, and that is indeed 1.5. So this just helps. If you can do this analysis quickly, you can quickly verify your question. Now they want you to do it graphically. So you do 8 sine 180x. Oh, it's going over and over again. It's really hard to see. We're going to take values that are slightly smaller and slightly bigger than the value, just so we can see it. So we can see that it goes from here to here. We can also confirm that the lowest value is indeed at 1.5, but we need to do it algebraically, which means we need to confirm if we were to plug this in. You might say, Peter, what if I don't? How do I do this without a calculator? Okay, fair enough. If you have the formula and you're trying to confirm without seeing the graph that you want to find the f of x value when t is 1.5. You simply take 8 sine 180 times, what was our t value? 1.5. And there's no other values. Our 1.5 represents our x, which means our f of 1.5 is equal to 8 sine. What's 1.5 of 180? It is 270. So you find your sine of 270. You discover that it is minus 1. Plug it into your calculator. Take 270 and press your trigonometry sine value, and you get minus 1. So we discover it's 8 times minus 1. That's what sine 270 is. Then you discover that's minus 8, which means when f of time is 1.5, y, if you want, or displacement, is minus 8. And we've already determined from our knowledge of graphs that that's the lowest point. So that helps us already. So now you've got to take a point that's just to the left, which is f of 1.49999, and you do that the same way. You take 8 sine 180 times 1.49999, and you're going to get a point that's just to the left. So you take your calculator and you do 180, and you multiply by 1.4999, and that's if I take all 4 nines. So that's 0.00001 to the left. And I hit equals, and I get 269.9982. Then I take the sine of that. So if we just take the value there, if I keep going, I'm left with f of 1.49999 is equal to 8 times the sine of this. So if I take the sine of that, I'm going to get very close to minus 1. And I get minus 0.999999. Now, I could write all that, but I'm just going to do f of 1.4999 is equal to 8 times minus 0.999999. Okay, and when I finish that, I multiply that by 8, I get this. So that means f of 1.49999 is equal to that. And I can just, for argument's sake, take as many decimal places as I have here. I think you're supposed to take twice as many for scientific when you multiply. I'd have to check that out, but we'll just do this. So that means I'm dealing with that. So to take the rate of change between that point, I have to take my f.15 minus my f1.49, rather, 999, and divide it all by 0.00001, which is the h I used to get 1.4999. So if I do that, I replace it with my actual values, which is minus 8 minus 7.99999, and I do believe I have to take more values. And that's where you should have kept the calculator in there. And I have to divide all of that by my h. So if you take your calculator, and you're going to discover that it comes out to this. And this is a big value to the exponent, times 10 to the exponent of negative 9. And then when you divide it by your h, you're going to get this. And you discover a number that doesn't look like it's close to 0, except that actually translates into, this is the same as minus 0. And what was the exponent? Let's look at the exponent. To the negative 4. So I forgot to add the negative 4, which is kind of important. So that means that is 3.94, let's say 784, times 10 to the power of negative 4. What does 10 to the negative 4 mean? It means that I'm going to take my decimal place and move it 4 to the left. So if I write it like this instead, I've got to take this decimal place here, and since it's to the power of -4, I move it 4 to the left. 1, 2, 3, 4, and I put it here instead. And then I get rid of all my other zeros, which means I'm dealing with this number. Is that number negative and close to 0? Yes. So if it is negative on the left side, if it's negative and on the left side, we know a maximum would be positive if on the left side. Since it's negative, we know that, and almost 0, we know that we're probably very close. So now the secret is when I take the right side, that should be positive and close to 0 and even close to that number. So that means I've got to do it all over again, but this time, and I'm just going to put this over here. This time, I've got to take a value just to the right of that. So I've got to take f1.5, 0, 0, 0, 1. And I've got to figure that out. It's 8 times sine of 180 times 1.5001. You take your calculator, and I'm just going to write this over and over and over. Then you take your calculator, and you multiply it by 180. And you take the sine of that, and you get that. And you multiply it by 8, and you get minus 7.9999. You get something like that. So when you're done, you get that. It's the same. It's the same. It's the same situation. And I forgot to copy the negative. That's all. But it's negative. So that means that the f of just to the right is this. So if I'm going to take the rate of change of that number, I've got to take the f of 1.001, which is to the right. I've got to subtract the f of 1.5. And I've got to divide it all by my h. And I've discovered it's minus 7.9999999, whatever, 605215, minus 8. And I'm going to get a value that's slightly positive. So if I take this, and I essentially add 8, I get this. Now you might say, oh my God, that's not a tiny number. And again, it's the same thing. And I'll just round up a bit. Oh, it's important to keep the exponent to the -9. So that's essentially times 10 to the exponent of -9. Which means if I rewrite this number with lots of zeros, 3947847, and I move the decimal place, which is currently here, I've got to move it 9 places to the left. So you can see that I probably did one of my h's too big here, because this is definitely moving to the left more. So I do 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's right about there. And you want to be exact in this, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, which means it's not there, it's actually there. Is this number positive? Yes, it is. Is it almost 0? Yes, it is. So we can see that if, since the rate of change just to the right of it is positive and 0, and the rate of change of the x value just to the left of it is negative and close to 0, that we must be dealing with a minimum value. Which means when time is equal to 1.5, that is indeed the minimum value, because time just to the left and right of it produces a rate of change that is positive and close to 0, and negative and close to 0, and on the right of it positive and close to 0, which means that 1.5, 8 is almost certainly the negative, which we already proved from our knowledge of graphs. So to answer the question, is this observation correct? Justify your answer using the appropriate change in displacement. Yes, it is correct. The weekly revenue of battery sales is based on the cost of batteries in X, and it's dictated by this downward-facing parabola that has a y-intercept of 30,000. The maximum revenue occurs when the package of batteries is $5. So they've pretty much told us that is the max. Write detailed instructions using the appropriate calculations of the rate of change in revenue to verify that the max value in the batteries is $5. Excellent. So here's your instructions on how to do it, and this might be worth writing down, because this is how you should do it for all rates of change. So you're trying to prove that it's a maximum, that $5 is the maximum value you should charge to the batteries to create the maximum revenue. In other words, that it is the vertex of this graph. Now, yeah, I could just complete the square and figure out the vertex, and if I do that right away and factor out -1, I can see right away that I get x squared minus 10x, and if I complete the square, I'm already kind of know that the vertex, partially completing the square, I can see that the vertex is indeed going to be +5 for x value. So completing the square here helps me verify that I'm on the right track. But here's the steps that you must do. I would say 1, roughly understand what graph you're dealing with. In this case, it's a downward facing parabola. Number 2, find f of 5, which in this case I believe is -25 plus 50 plus 30,000 plus 500. No, plus 50, which is 30,025. Okay, so that tells me that it's not, they're pretty much at max value when they're at the y-intercept. Step 2, choose your h, and we're going to set it at, you can choose anything you want. Generally speaking, the more zeros here, the more accurate you're going to get. But we'll just keep a value that's simple. Find a value of r of t. So in this case, I should say r of t, or r of x, just to the left of 5 using your h. So we would find r of 5 minus h, which is the same as r of 4.999. So we need to find r of 4.999, which means you would find it by putting it in the calculator. Okay, minus 4.999 squared plus 10 times 4.999 plus 30,000. So that's your next step, and you discover that that is, and here's where you need a calculator. So what's 4 point, oh, and I'm going to have to stop after this one, squared, and it's negative, and then I add, what's 10 times 4.99? 4.4999, and then I add 30,000. And you're going to get a value that's very close, but it should be slightly smaller than your actual vertex. And that's a big hint right there, that this is slightly smaller than this. Now you're going to find your rate of change between those points, between your r of 5 minus your r of 4.999, which is to the left of it, divided by h, and you're hoping it's going to be, since we're dealing with a max value, positive and close to 0. Okay? And when I do this, when I punch my actual numbers in, I get, so this is step 5, find rate of change between these 2 points. And I find it, and I discover it's this, which, by the way, was, yeah, was that. And I subtract the FR5, and I get that. And then I divide it by my rate of change, 0.001. Now, my rate of change is a little less accurate because I used a small h. But I do indeed find that, oh, it should be positive or negative? it should be positive. Yeah, and I subtracted the wrong ones. It should be 30,025 minus 30,024.99999. So I did it the wrong direction. So that means if I'm going to do it properly, let's do it again. And that just goes to show how easy it is to get the wrong thing. The reason I've got to do the first one first is because it's to the right. R5 is to the right of R4.999. So I subtract it, and I get minus 30,024.99999. And I get this, and then when I divide it by my h, I get this. It's positive. So I indeed get a positive number, 0.0001, which is close to 0 and positive. Then you've step 5, find a value of r of x just to the right of 5 using your h. And you do the same thing. You're going to have to find r of 5 plus h. Okay? Then finally, step 6, find your rate of change between r5 plus h and r5 divided by h, and you are hoping it is negative and close to 0. Finally, if all of that is true, then you have found the max value, i.e. vertex, max revenue, is indeed when x equals 5. And this is just to teach you how to express mathematics verbally. And we've all encountered the difficulties in interpreting these puzzles. Explain how to determine the value of x that gives a maximum for this. Sine value. Yeah, just give me a second. And then the speedometer of the cars, this, and I'm just going to have to stop.